We are in section 10.3, polar coordinates. Polar coordinates are a system that was introduced by Newton and very useful in a lot of different areas of mathematics, engineering, and sciences. And so with this, there's a lot of information to write down. So the first thing that we have is a pole, and a pole you can see is going to be at the origin for us in this graphing system. And so for that, we have a couple other things. The first one's going to be r, and r is going to be, think of it as a radius. This is the distance from that pole to point P. And then we have theta, and you can see theta also on this graph, and theta is going to be an angle. It's in standard form. What standard form means is that your initial spot, your initial side that makes this angle down here is going to be on the positive x-axis if you think about it with our normal coordinate system. And so you can see too that with theta, theta can either be positive or it could be negative. And positive is going to be in a counterclockwise direction, and then negative would be in a clockwise direction. And so again, in standard form would be that where that initial side is going to be on the positive x-axis. And then you would figure out the size of that angle by going to that side that we have, that terminal side R, where it is connecting the pole to point P. So down below we have polar coordinates, and those are written as r and theta. And again, r is that radius or that distance from the pole to P, and theta is going to be that angle that measures between the initial and the terminal sides that create the angle. And so a couple things here, kind of copying down what we had up above with our pole and our initial side. And then we also would have, so it would be our r and our theta, and this point that we have here that we called P up above. I'm going to define it now as r comma theta. And so we have this idea of a negative r value, and what that negative r value means that that terminal side that creates that angle is going to reflect through the pole and on the other side. And so doing that, that would be like down here. That distance would still be the same. And so this distance here would match the distance for r. And so this would also be a length of r, but because we reflected it through, this is going to be, instead of a positive r value, it would be a negative r value, comma theta. And so in order to think about this, you would have taken your theta and added 180 degrees or pi to it. And so to do this, we did theta plus pi. So in addition, I also have on here is a polar coordinate system. And so that polar coordinate system, you'll notice that it's created, it looks almost like the unit circle. However, it has a bunch of different circles on it. And those are going to have different radius depending on what is given. And so, but the idea behind it is very similar to the idea of a unit circle. So we'll discuss this idea more in class. The example on the next page says, to plot the points whose polar coordinates are given, then find two other pairs of polar coordinates of the point, one with r greater than 0 and another one with r less than 0. So the first one that we have is going to be 0.1, 7 pi over 4. And so with this, we know that r is going to be 1, and our theta is going to be at 7 pi over 4. So thinking about this, I'm going to make a circle with the radius 1. And 7 pi over 4 is going to be in quadrant 4. And so our theta, which would go all the way around like this, I'll label that theta, is going to end at 7 pi over 4. And that radius there is 1. So we have our 0.1, 7 pi over 4. So now we need to find an additional point that also has a radius that is going to be greater than 0. So since we already defined this as 1, that radius needs to stay positive 1. And so if you think about it, we've dealt with circles before and back in trig, talking about angles, and if you were to add another circle to this, you would be ending at the same exact spot. And so remember that an entire circle is going to be adding or subtracting even 2 pi. So when r is greater than 0, our radius is going to be 1, and then we had 7 pi over 4, and you can either add or subtract 2 pi, and I'll just go ahead and subtract 2 pi, but it doesn't matter. They both are going to work out the same, so you can see that there would be a lot of equivalent solutions for this. So we have 1 comma negative pi over 4, and that's going to be an equivalent point on our polar coordinate system. So now another one is going to be, we need to find when r is less than 0. So when r is less than 0, this time we are going to have negative 1. And so like we said, this is going to reflect through. And so reflecting through would be causing 180 degrees or a pi change in that theta value. And so I have my original angle, which is 7 pi over 4. And I am going to subtract pi. And so this is going to be negative 1 comma 3 pi over 4. So plotting that 3 pi over 4, since the radius on this problem is negative when we rewrote it as negative 1, that means that that point is going to reflect through the pole and into quadrant 4, which is where that original point at 1 comma 7 pi over 4 is. So we have another example, B. This time r is equal to negative 3 and theta is equal to pi over 6. Sketching the polar coordinate plane, I know that the radius is 1 negative, but it's also 3. So if I make, our radius has to be 3, so I need to make 3 circles to show that that is actually what that radius is. So making my third circle is going to be where that point would be on. Pi over 6 is a small angle, so we would have right here would be pi over 6, but this would be with a positive angle. So I'll connect that point from the pole. And so again, remember that since we have a negative 3 for our radius, this is going to reflect through the pole and into quadrant 3. So we have negative 3 comma pi over 6. So again, we need to figure out the radius being greater than 0. And so if the radius was greater than 0, we would have a positive 3. And again, I need to end up at that final spot, which is negative 3 comma pi over 6. And so in order to do that, if I had the positive angle, you can see that, which is plotted over here on the right, you would have to add pi to your original angle. So we have pi over 6 plus pi, and we would get 3 comma 7 pi over 6. Likewise, looking when r is less than 0, that means that our radius would stay negative. And again, we would add a circle or subtract a circle. Since we subtracted a circle in the last one, I'll add a circle to this one. Again, it doesn't matter, but we have pi over 6 plus 2 pi. And so this would work out to be negative 3 comma 13 pi over 6. So part C, I'm going to circle, and we'll look at this one together in class, but definitely give it a try on your own to see if you can plot it. Remember that r is equal to 1 and theta is equal to negative 1. And this is negative 1 radians, and so you can convert that to degrees if that makes it a little bit easier to think about where that would be located. So right below it says converting polar coordinates to Cartesian coordinates. And so if you go ahead and sketch this on a Cartesian coordinate plane, you will have an x and y axes, and then I'm going to go ahead and put in r, my radius, and theta, which is describing how far r is. And then we need to talk about what we have for our sides of our triangle. And so down here, we're going to call this distance here x, and the vertical distance here on the triangle y. And so we know a few things. We know that sine of theta would be equal to opposite over our hypotenuse. So we have y over r, or y is equal to r sine theta. And so we are able to take r and theta and find our y value and change that from a polar coordinate to a Cartesian coordinate. Likewise, we know that cosine of theta is equal to x over r. And likewise, we would say x is equal to r cosine theta. And then we also know that, we know that r squared is equal to x squared plus y squared using our Pythagorean theorem. And then also tangent of theta is equal to y over x. So all four of these boxes, these equations that we have written down, need to be memorized for your upcoming exam, so make sure you know those. And then we have an example right after this that says, plot the point whose polar coordinates are given, then find the Cartesian coordinates of that point. And so we'd be using those formulas that we just wrote down. And so the first one on here is negative square root of 2, and our angle is going to be 5 pi over 4. So again, this is r, and this would be theta. And so at first it says to plot the point. And so plotting the point, rad 2 is approximately, it's in between 1 and 2, so 1.41. And so I'm going to go ahead and make sure I draw two different circles, one with a radius of 1, one with a radius of 2. And it is negative, so we do need to talk about that. But let's just assume r is positive right now. But our angle is 5 pi over 4, which is going to be in our third quadrant. And that radius is at rad 2 over here. And so again, this would be our point, positive rad 2 comma 5 pi over 4. But since it is a negative r, that's going to reflect through that pole and into quadrant 1. And so our point would be at negative square root of 2 comma 5 pi over 4. And in order to find our Cartesian coordinates, which is what it wants us to find here, we know that in order to find x, the formulas that we just wrote down is x is equal to r cosine of theta. And to find y, we have r sine theta. And we know that r is equal to negative square root of 2. And our angle is going to be 5 pi over 4. And so from our unit circle, our trig formulas that we have, cosine of 5 pi over 4 is going to be negative rad 2 over 2. So working this out, we do get 1. Likewise for y, we have r, which is going to be negative square root of 2, times sine of theta, which is also negative square root of 2 over 2. And working this out, we get 1. And so this corresponds to a Cartesian point, which is going to be 1 comma 1, or x comma y, which is 1 comma 1. And if you look at that, it looks as though it is, I know, our rough sketch by hand, but 1 comma 1 is where that would be. So then the next thing that we have is 1 comma 5 pi over 2. And so we have r and theta. And so first sketching it, the radius of the circle is just 1. We are dealing with a positive radius. This time though, our theta is actually going to create a whole entire circle. It's 5 pi over 2. So our theta would go all the way around once, which would be 4 pi over 2, or 2 pi, and then another half. So that would be theta. So it does end up here. And so our point is going to be at 1 comma 5 pi over 2. And again, that is our polar coordinate is 1 comma 5 pi over 2. And changing this to a Cartesian coordinate, we are going to have x equals r cosine theta and y equals r sine theta. Substituting in r, we have 1 times cosine of 5 pi over 2. And 5 pi over 2, or you can think of it as cosine of pi over 2 is just 0. And so we get 1 times 0, which is 0. And likewise for our y value, we're going to have r, which is 1 times sine of 5 pi over 2, or think of it as pi over 2, which is just 1 when you take sine of pi over 2. So 1 times 1 is 1. So our Cartesian coordinate is going to be 0, comma 1. And likewise, looking at that, you can see that that does look as though it would be 0, comma 1. The third one I'm going to go ahead and circle, and we will work on this one together in class. But definitely give it a try on your own. Right below this says to sketch the region in the plane consisting of the points whose polar coordinates satisfy the given conditions. So this time we have a range of values for r, and we have a range of values for theta. I'm going to sketch my polar coordinates, and r can take on values between 0 and 2. So there's 1 for my radius and then 2 for my radius. And theta is going to be between pi and 3 pi over 2. And so shading this whole area, so it says sketch the region, it would be between pi and 3 pi over 2. It would be all of this. And so again, the radii could be between 0 and 2. The second one says that r is going to be between 1 and 3, and theta is going to be between pi over 6 and 5 pi over 6. So sketching this on our polar coordinate plane, since the radii is going to be between 1 and 3, I'm going to make 3 circles. So one with a radius of 1, the next with a radius of 2, and the third one with a radius of 3. And since our theta is between pi over 6, which would be out in the first quadrant, and 5 pi over 6, which is in the second quadrant, and since this can take on any r value between 1 and 3, I'm going to go ahead and draw those on here, and we're going to shade that region between 1 and 3. And so this will be the region that is satisfying these conditions that we have. The example on the next page says to identify the curve by finding the Cartesian equation for the curve. So part A says r equals 4 secant theta, and we know that r is equal to 4 times secant is the same as 1 over cosine of theta, and then we know that we can multiply both sides by cosine of theta, and we would have r cosine of theta would be equal to 4. And from our formulas earlier that we derived, we know that r cosine theta is equivalent to x. So this is equivalent to the equation x is equal to 4. And so this is just a vertical line. Part B says theta equals pi over 3. If you notice, this time we don't have any trig functions in it. So I'm going to go ahead and put one in, and if you do that to one side, you have to do it to the other. So I'm going to go ahead and say tangent of theta is equal to tangent of pi over 3. And tangent of theta from our formulas is y over x. And from our unit circle, tangent of pi over 3 is just rad 3 over 2 over 1 over 2, or rad 3 over 1. And so multiplying both sides by x, we get y equals rad 3 times x. And remember, tangent of pi over 3 would be the same as sine of pi over 3 divided by cosine of pi over 3. And so this is a line, and it would pass through 0, 0, and has a slope of the square root of 3. So part C, we're going to work on together in class, but if you notice there is a tangent theta, secant theta, so a good idea would be to change everything into sines and cosines, so definitely give it a try on your own. The example right below this says, to sketch the curve with a given polar equation by first sketching the graph of r as a function of theta in Cartesian coordinates. So we have r equals 1 minus cosine of theta. And so in order to do this, I'm going to create a table of values with theta and with r. And so I'm going to select some values of theta. So I'm going to say theta can be 0. I'm going to go ahead and use pi over 2, pi, 3 pi over 2, and 2 pi. And see if I need additional points, then I can find those. But substituting this in, we have cosine of 0, which is 1, and 1 minus 1 would be 0. So radius of 0. And then we have 1 minus cosine pi over 2, which is going to be 1 minus 0, or 1. Cosine of pi is negative 1, so 1 minus negative 1 would become 2. And likewise, finishing up at 3 pi over 2, we would get 1, and 2 pi we would get 0. So going ahead and plotting these, I would have, so first plotting this on a, as the direction said, on a Cartesian coordinate plane versus that polar, that circular polar plane that we have. So we would have theta here and our r values here. And looking at pi over 2, pi, 3 pi over 2, and 2 pi. And again, this would continue on. And so for this, we would have 0, 1, and 2. So at pi over 2, we have 1. At pi, we have 2. Back at 1, and then back down here at 0. And as this continues, so this is like what we would have seen before in like a trig class as we graph those. And so this is going to be Cartesian coordinate system. And so we're going to graph this again, but in the polar coordinate system. And so going ahead and doing this, looking at what we have, we know that r is 0, 0. So that's that pole here. At pi over 2, we would have 1. And at pi, we would have 2. At 3 pi over 2, we have 1 also. And at 2 pi, we're back at 0. It looks kind of odd since it makes straight lines. So I'm going to explore what happens if we had pi over 4 and negative pi over 4. And so with this, I would have 1 minus, and cosine of pi over 4 is rad 2 over 2. And so on a calculator, you would get 0.29. And so at pi over 4, we would have 0.29. And then likewise with negative pi over 4, we have 1 minus rad 2 over 2, which is again 0.29. And so what this is going to make, connecting these, and so this shape that we have, we see very often in many applications, and this is called a cardioid. And again, this is our polar coordinate system. On the next page, we have another example. This time r is equal to ln of theta, and it tells us that theta is greater than or equal to 1. So we're going to go ahead and do the same exact thing like we did and create a table of values. So for theta and for r. And so for this one, I'm going to go ahead and put down some values at theta. It says theta has to be greater than or equal to 1. And then from there, I'm going to go ahead and do pi over 3, pi over 2, 3 pi over 4, pi, 5 pi over 4, and it's up to you to pick whatever values it is that you need. I'm going to continue this on and do 3 pi over 2, 7 pi over 4, and 2 pi. And again, like in the last example, if we need additional points, we can always substitute in different values of theta. So ln of 1 is just going to be 0. And then for this, make sure you have your calculator set for radians. And we're just going to substitute these in. I'm going to round 2 decimal places. And so pi over 3, ln of pi over 3 is 0.05. ln of pi over 2 is 0.45. ln of 3 pi over 4 is 0.86. ln of pi is 1.14. We get 1.37, 1.55, 1.70, and ln of 2 pi is 1.83. So graphing this first on our Cartesian coordinate plane, where we have theta and we have our r value, we are going to be starting this at 1, and plotting these all is a little difficult, but looking at some of these, I'll put down pi over 2, pi, and then 2 pi, just so we can see how this is progressing. So at 1 we do have 0. At pi over 2 we have 0.45. So I'll go ahead and put some values on the r axes that we have. And so at pi over 2, 0.45. At pi we have 1.14. 2 pi we have 1.83. And so connecting these, and again this is going to be in terms of our Cartesian coordinate plane. So now graphing this on our polar coordinate plane, we're going to have at theta being 1 we have 0, and at pi over 3 we have 0.05, at pi over 2 we have 0.45, at 3 pi over 4 we have 0.86, at pi we have 1.14, at 5 pi over 4 we have 1.37, at 3 pi over 2 we have 1.55, at 7 pi over 4 we have 1.70, and at 2 pi we have 1.83. And so connecting these, and this would continue. I'll draw that with an arrow tip. You can definitely continue as it circles out, and this also has a special name. This is Archimedes spiral. And Archimedes spiral has a lot of uses and a lot of different applications, such as art, in science, and in a lot of nature applications. So we have a summary of polar curves, so definitely take some time to look through these. Nothing that you have to have memorized, but definitely know and understand different shapes that could occur. On the next page, we have tangents to polar curves. And so this says to find the tangent line to a polar curve r equals f of theta, we regard theta as a parameter and write its parametric equation as x equals r cosine theta, or f of theta times cosine theta, and y equals r sine theta, or f of theta times sine theta. Then, using the methods for finding slopes of parametric curves and the product rule, we have dy dx equals dy d theta over dx d theta, or dr d theta sine theta plus r cosine theta, which would be using that product rule, over dr d theta cosine theta minus r sine theta. And again, with horizontal tangents, this is going to occur when dy d theta is equal to 0, provided that dx d theta does not equal 0. And vertical tangents, which is going to be when dx d theta equals 0, provided that dy d theta doesn't equal 0. Note, if we are looking for tangent lines at the pole, then r equals 0, and the above equation simplifies to dy dx equals tangent of theta if dr d theta doesn't equal 0. So we have an example right below that says find the slopes of the tangent line to the given polar curve at the point specified in the value of theta. So it says r equals 2 minus sine theta, where theta is equal to pi over 3. And so the first thing that we have is going to be that x is equal to r cosine theta, and r for this problem is equal to 2 minus sine theta, and times cosine theta. And our y value is equal to r times sine theta. And again, r is equal to 2 minus sine theta times sine theta. And so dy dx is equal to dy d theta over dx d theta, which is going to be equal to, and taking the derivative of y with respect to theta, we use the product rule. And so we're going to have the first term, which is going to be 2 minus sine of theta, times the derivative of sine of theta, which is cosine of theta, plus the second term, which is sine of theta, times the derivative of 2 minus sine theta, which is going to be negative cosine theta, over, and then the derivative of x with respect to theta is going to be our first term, which is 2 minus sine theta, times the derivative of cosine, which is going to be negative sine theta, and put the negative out in front, plus the second term, which is cosine of theta, times the derivative of the second, which is going to be negative cosine of theta. So simplifying this, we end up with 2 cosine theta minus, and then distributing our cosine to sine, you'll notice that we have a negative sine theta cosine theta and another negative sine theta cosine theta. So I'm going to say minus 2 sine theta cosine thetas over, and then likewise in our denominator we're going to have a negative 2 sine theta, and then we also have a sine theta times sine theta, and also with the negative, so it's going to be plus sine squared theta. And then we have a minus cosine squared theta. So a few things to note. The first one is what we have up here in the numerator, which is 2 sine theta cosine theta, and this is equivalent to sine of 2 theta. And then in the denominator, we have sine squared theta minus cosine squared theta, which is going to be equal to cosine of 2 theta. And so this works out to being 2 cosine theta minus sine of 2 theta all over negative 2 sine theta plus cosine of 2 theta.